Welcome back, everybody. Today we're going to keep adding to our integration toolbox. Last time we saw this new formula called integration by parts, which allowed us to kind of undo the product rule. Today we're going to not so much see like a new formula that we can make use of, but more see a couple of different strategies that we can use to help us integrate when our functions involve products of sines and cosines. And helping us out in these strategies are a number of different trig identities. And so let's take a moment and go through those before we dive in and see how these strategies work. So to start, if one trig identity comes to mind, it's probably this one, cosine squared plus sine squared equals 1. Pop quiz, why is this equation true? So the reason is geometric, right? Here's the picture that I have in mind thinking about this identity, right? Cosine and sine deal with the unit circle, right? If we have the unit circle, right, there it is. Right, if we give a certain angle, then the x-coordinate of the point we get, right, that's cosine, and the y-coordinate is sine. And well, the equation of the unit circle is x squared plus y squared equals 1, right, just coming from the Pythagorean theorem. And so right there, subbing in for x and y, we get cosine squared plus sine squared equals 1. And so because of that, I like to call this identity our Pythagorean theorem identity. And what this identity is going to be used for us is as a way to take a cosine squared, if that comes up, and swap it out for something involving sine squared, right? Specifically solving by tossing this over, it would be 1 minus sine squared. Right? And it also works vice versa. If we have a sine squared, well then we can use this equation to swap that out with something involving cosine squared. Now these formulas on the right, these are what are called double angle formulas. And the way that these are going to be used is to reduce the power on our trig functions. So specifically, if you notice here on the left, we have a sine squared. And over on the right, we have this ugly thing, but it involves cosine to the first power, right? So the exponent on our trig function has dropped. And similarly here, at the bottom as well, we have cosine squared, and that gets replaced with some stuff with the trig function, again, to the first power. And that's going to turn out to be useful for us in terms of integration. Notice also these are very similar formulas. The only difference is the one with both cosines has a positive instead of the negative. I like to think of it as this cosine squared is happy that it's going to see another cosine, and so plus instead of minus, I guess. It doesn't make much sense, but that's how I think of it. And just a few times of writing these down, you'll have them memorized for sure. All right, over here on the side, used a little bit less frequently are these other trig identities. Since we are just gathering this big box of trig identities, I wanted to mention them. If we take this Pythagorean theorem identity and divide everything by cosine squared. Then we get this identity involving tangent and secant, right? Cosine squared divided by cosine squared is 1. Sine squared over cosine squared is tangent squared. And 1 over cosine squared is secant squared. And then down here, sine of 2x equals this stuff on the right. We're going to be making use of that next time to take something involving this angle 2x and write it in terms of these trig functions just involving that angle x. All right, so that's our bag of trig formulas. Let's take a look at the strategies that we're going to be using. All right, so the integrals that we're going to be thinking about today are these integrals where we have some power of sine times some power of cosine, and inside sort of this family of functions are also the integrals with just sine and just cosine. Right, you can imagine either the n or the k being 0 to make that happen. So we're talking about these as well. And the two cases that we're going to think about and be able to have a strategy to deal with depend on these exponents. And so here, case 1 is if both these exponents happen to be even. And if that's the case, then we're going to use our double angle formulas like crazy just to boil everything down as much as we can until we can integrate. Let's see how that plays out. All right, so here's our integral. Sine to the 4th, no cosine here, but notice each power that we see is even, and so we're in this situation. Our double angle formula doesn't involve sine to the 4th, it involves sine squared. And so our first step, minus, right, because it's not the cosine, cosine 2x. Our first step is to make a sine squared appear. And the way that we can do that, since this is an even power, is we can write this as sine squared of x to some power. In this case, that power has to be 2, since 2 times 2 gives us the 4. At this point, we can now swap out the sine squared x for what it equals over here from the double angle formula. We'll then have some more work to do, some algebra, and even some past that. But let me encourage you to right now pause the video, make this substitution, and see how far you can get in terms of working out this integral. All right, well, let's see how this goes. Once we make that substitution, here's what we get. And so this squared up here is going to distribute nicely. So we have a product inside. Distribute to the 1/2 and to the 1 minus cosine 2x factor. Over here, 1/2 squared is 1/4, and we can slide that out front. There that is. And then what's left over here, 1 minus cosine 2x squared. We'll then just need to FOIL that out. So 1 times 1 gives us 1. We'll have 1 times negative cosine times the 1. That'll give us the minus 2 cosine 2x down here in the middle. And then the negative cosine times the negative cosine give us positive cosine squared of 2x. And so this is what things look like when the dust settles. And in terms of integration, we're all set to integrate the term 1. This term in the middle, I claim we can actually integrate just because the power here on the cosine is 1. We can figure out the antiderivative there. But over here on the right, the power is 2. right? So we do not yet know what the antiderivative for this term is going to be. And so our attention's kind of focused in over here on this last term, but notice looking at it, it's an even power of cosine, right? And that's exactly the situation that we're thinking about. And our strategy is still the same. We want to use our double angle formula. But here I'm going to write it in a more general form, because here we don't just have cosine of x, we have cosine of 2x, right? And so let's think about our double angle formula in a general way, right? The original formula had cosine squared of x, but that x is just a placeholder. So let's write box here. So the formula is then 1/2 1 plus cosine of 2 box, and I'm running out of space, and so let me kind of swing down a little bit. 1/2 1 plus cosine of 2 times box. All right, this is our general way of thinking about our double angle formula. But here, what's actually going to go inside this box is 2x. That's what we have. And so on the right-hand side of our formula, we'll have 2 times 2x, or cosine of 4x at the end of the day. All right, and so here's us working through that, and then I've just distributed the 1/2 to each of these pieces. And so this is what our blue box becomes. And notice if we want to, we can take this 1/2 and kind of bring it over and combine it with this other constant 1 hanging out. So 1 plus 1/2 would be 1.5 or 3/2. And so here's what we are looking at now with the dust settled. We have our 3/2, then our middle term just copy pasted, and then we have our 1/2 cosine 4x. And I claim that we are now in a great spot to go ahead and integrate all 3 of these terms. Right, 3/2, just a constant, so integrates to 3/2 x. Now over here in the middle, I have a little bit of work to do, but I claim that since the power on the cosine is just to the first, we can antidifferentiate the middle term, and similarly, since the power of cosine is to the first, on the last term, we can integrate that as well. And so in the middle, we could maybe do like a u sub off to the side or something like that, but we can also just kind of by hand construct the antiderivative through a little trial and error. The idea is, thinking about how the chain rule works, if we're going to have an antiderivative to this thing, well, as its kind of main piece, it's got to have a sine of 2x in there, right? Just because sine is a function whose derivative is cosine, and since we have a negative out here on the left, let's include that. And let's just see what happens here. If we take the derivative of sine of 2x, we'll get with the negative out front, we'll get negative cosine 2x, and then with the chain rule, we'll get times 2. And notice that's exactly what we have here. Negative cosine 2x times 2. And so this kind of first guess at the antiderivative actually turned out to be exactly what we need. And so that's what we can write down here as our antiderivative. All right, let's think about this term over on the right now. Once again, using this kind of same idea, any antiderivative for this thing is going to have as its kind of main piece, it's got to have a sine of 4x going on, right? And so this is kind of maybe our first guess. And now we can test that, see what happens when we take the derivative. Well, taking the derivative, we'd get a cosine of 4x times 4. And if we look back at what we're trying to get, we're happy with the cosine of 4x, but we're not so happy with the 4, right? We wanted to get 1/2. And so what we'll want to do is scale our guess by something so that instead of seeing 4, we actually see 1/2. And what's going to make that happen? 1/8. Right, then in our derivative, we'd get this 4 times 1/8, which would simplify down to the 1/2 that we want to see. And so with that, we have our antiderivative to our last piece, and we can toss a plus c at the end. And right there, those are the antiderivatives for sine to the 4th, the function that we started with. Now, sine to the 4th doesn't have any cosines involved, but this strategy that we just made use of, just using our double angle formulas as much as possible until we can integrate, this definitely works if we have both sines and cosines, as long as both powers are even. All right, so that was case 1, the strategy that we can use when both our exponents are even. Our next case is if at least one exponent is odd. And in that case, maybe they're both odd or maybe just one is. Let's just say that one exponent is odd. Then we'll focus in on that piece, and what we're going to do is 3 steps. We're first going to pull off one of those factors from that odd pile. We're going to use the Pythagorean theorem identity on what we have left there, and then we're going to do a u sub. And I'll ask you just to go with me for now. I'll look to clarify the point of all this, what this is trying to accomplish as we work through an example. All right, so here, the example we're looking at is integrating sine to the 5th times cosine to the 6th. And notice that indeed, one of these exponents is odd, and so we'll focus in on this pile of sines. And following the instructions here, let's pull off one of those sines, not bringing it outside the integral, but just bringing it over to the right. Once we do that, there it is. And what's left is sine to the 4th. And so at this point, we've done step 1. Step 2 here is use the Pythagorean theorem identity on what's left. Well, in order to do that, what's left over here, since we pulled off one of these sines, we now have an even power. And so we can do the trick that we saw just a moment ago and write this as sine squared to some power. However, now, we don't want to use a double angle formula. The instructions here are telling us to use Pythagorean theorem identity. And so here, sine squared is 1 minus cosine squared. And making that substitution, this is what we're left with. And it looks horrible. It looks absolutely awful, but I claim this is actually something to feel good about. we are happy with where we're at because of the structure of what we have going on here. Specifically, what I'm talking about is this. We have this piece over here on the left that's all in terms of cosine of x. And over here on the right, we have more or less cosine's derivative. Right? We have this sort of structure going on. And in this situation, what's going to work great is a u sub, right? If we do a u sub with u equals cosine of x, then the stuff in the cloud will collapse nicely, and the derivative of cosine, right, sine over here, it's off by negative, but that'll get eaten up with the du. So we're actually in a good spot. And so, once again, maybe I'll say, pause the video at this point, see if you can work out this u sub and the rest of the integral here. Take a couple minutes and see what you can do with it. All right, so working through this substitution, right, if u is cosine of x, then du is negative sine dx. And here we see the sine dx in our integral, and so we can just take that negative and toss it on over. All right, this becomes negative du is sine of x dx. And so the stuff in the box becomes negative du, and that negative can slid out just right out front. And inside, wherever we see a cosine, it's going to get swapped out with u, right? And so here, cosine squared, that becomes u squared. Cosine to the sixth becomes u to the sixth. And this looks a little bit better. At least there's no trig going on. But I claim we're actually in a really good spot. Here, I claim that what's kind of hidden here, this is a polynomial in u. It's just all factored. So if we want to integrate this thing, we actually want to spread this out. We want to distribute everything that we can so that we can see the polynomial that we are actually looking at. And so here, for this term on the left, we just want to work this out. And again, thinking through, just foiling this out, we'll have 1 times 1, which will give us 1, and then 1 times negative u squared times 1. So we'll get minus 2u squared, and negative u squared times u squared. Give us positive u to the 2 plus 2, which is 4. And then all of that times the u6 that's still hanging out on the right. Right, and so then we'll take that u to the sixth, and we'll want to distribute it to each of these terms. Get u to the sixth on the left. And over here, we're going to get u squared times u to the sixth. And those exponents are going to add. Right, so we'll get u to the eighth, and then for the last term, u to the 10th. At this point, with everything spread out, we can now just kind of term by term go through and integrate this polynomial in u. Just adding 1 to the exponent, dividing by that new exponent. Here's what we end up with. And the last thing to do is take those u's and swap them out for what they are in terms of x, right? Just using our u sub from a few minutes ago. And with that substitution, here is what we end up with. So those right there, those are the antiderivatives to the function we started with, sine to the 5th times cosine to the 6th. And so this strategy that we just made use of here for our integral, right? It involved this integral where we had sines and cosines. The strategy does still work if we just have an integral with cosine or just with sine. Again, if that has an odd power, we'll be able to work through it. To wrap up today, I just wanted to mention that with these strategies, there's a little bit of flexibility that comes with them. And what I mean by that is, sometimes if we have an integral, it might not be literally, a product of sines and cosines, but sometimes we can still get these ideas to work. So for example, maybe we have something like a quotient of sines and cosines. Maybe we have like sine to the 7th over cosine of x dx. Well, here I claim that we can still kind of make use of our strategy for when one of our powers is odd and try and kind of get this to work through. Another useful thing to keep in mind is sometimes if our integral involves tangents or secants, we can actually take that integral and kind of rewrite things and sometimes land looking at a function that we now know what to do with. And the way that we can kind of translate things is by replacing everything in terms of sine and cosine. And so here I'm just talking about, right, using the definition here of tangent as sine of x over cosine of x, and secant of x is 1 over cosine of x. And so sometimes if we have tangents and secants floating around, we can make these substitutions, and when the dust settles, we'll actually have something that we know what to do with. All right, well, that's it for today. Good work, everybody. If you have any questions, post those to Piazza, and I'll see you next time.